March 6, 1944. 6 miles above central Germany, Major Don Blakesley leads 357 P-51 Mustangs deeper into German airspace than any Allied fighter had ever ventured. Their target, Berlin. The city Hitler had declared unreachable by Allied bombers. For the first time in aviation history, long-range fighters could protect bombers all the way to the Nazi capital and back. This unprecedented mission was possible because of an impossible fuel mixture engineered by a German immigrant who had transformed his aircraft design into the ultimate weapon against his homeland. The engineer was Edgar Schmude, a self-taught Austrian-born designer working for North American Aviation in Los Angeles. The fuel was 150-octane aviation gasoline, a blend so volatile and powerful that military engineers had declared it too dangerous for operational use. The combination would revolutionize aerial warfare and give the Allies decisive air superiority over Europe. This is the story of how one man's impossible fuel mixture changed the course of World War II. To understand why high-octane fuel mattered so desperately, you must first understand the crisis facing Allied bombers in 1943. American flying fortresses and liberators were flying daylight raids deep into German territory without fighter escort. German interceptors destroyed bomber formations with impunity once Allied fighters reached the limits of their range. The Schweinfurt raids of October 1943 epitomized this crisis. 60 bomber aircraft were destroyed in a single mission. Crew losses exceeded 25%. Without long-range fighter protection, daylight bombing operations against Germany were unsustainable. The problem was not aircraft design but fuel limitations. Existing fighters like the Republic P-47 Thunderbolt and Lockheed P-38 Lightning consumed fuel too rapidly for extended missions. Standard 87-octane aviation gasoline limited engine power and efficiency. Higher power settings required better fuel to prevent engine detonation and mechanical failure. Military engineers understood the physics but considered high-octane formulations impractical for mass production and field operations. Edgar Schmude had been wrestling with fighter range limitations since 1941, when North American aviation began developing the P-51 for the Royal Air Force. Born December 30, 1899 in Hornbach, Bavaria, Schmude had immigrated to the United States in 1931 with revolutionary ideas about aircraft design. His laminar flow wing concept promised exceptional efficiency, but realizing its potential required engines operating at power levels impossible with standard fuels. Schmude's journey to America had been driven by economic necessity and engineering ambition. After serving as a mechanic in the Austro-Hungarian aviation troops during World War I, he witnessed the transformative potential of aircraft technology. The post-war economic collapse in Germany motivated his emigration, first to Brazil, where he worked for General Motors, then to the United States, where he joined Fokker Aircraft Corporation, before moving to North American Aviation in 1936. The breakthrough began in January 1943, when the Army Air Force's Materiel Command initiated testing of experimental 150-octane aviation fuel. Traditional gasoline used octane ratings between 87 and 100. The new formulation promised unprecedented anti-knock properties that would allow engines to operate at manifold pressures previously considered destructive. Initial tests suggested power increases of 15 to 20% over standard fuels. The development of high-octane aviation fuel represented a convergence of chemistry, engineering, and strategic necessity. Petroleum refiners had been experimenting with aromatic compounds since the late 1930s, but military applications required solving problems of production scale, quality consistency, and field logistics that had never been attempted. The chemistry involved blending complex hydrocarbon molecules in precise ratios to achieve optimal anti-knock characteristics, while maintaining stability under extreme temperature variations. Laboratory testing revealed promising results, but translating those findings into operational reality required overcoming numerous technical obstacles. The fuel had to remain stable during long-term storage in various climates, from the Arctic conditions of Alaska to the tropical heat of Pacific Islands. It needed to flow properly through fuel systems at high altitude, where temperatures dropped far below freezing. Most critically, it had to maintain consistent performance characteristics across thousands of gallons produced by different refineries using varying crude oil sources. Schmude recognized immediately that high-octane fuel could transform his P-51 design from a capable interceptor into the world's premier escort fighter. The aircraft already featured exceptional aerodynamic efficiency and innovative wing fuel tanks that provided superior range compared to contemporary fighters. Enhanced engine power would improve climb performance, maximum speed, and fuel economy simultaneously, extending operational radius beyond anything previously achieved. The engineering challenges were immense. 150-octane fuel contained aromatic compounds that attacked rubber components in standard fuel systems. Fuel lines, gaskets, and tank linings dissolved when exposed to the new formulation. Engine modifications were equally complex. Higher octane ratings enabled increased manifold pressure, but engines required strengthened components to withstand the additional stress. Spark plugs fouled rapidly due to increased lead content. Fuel injection systems required recalibration. Schmude assembled a specialized team to tackle each problem systematically. The fuel chemistry represented a breakthrough incorporating complex aromatic compounds, including toluene and xylene, that dramatically improved anti-knock characteristics. However, these compounds proved devastatingly corrosive to existing aircraft fuel systems. Standard rubber fuel lines dissolved within hours. Fuel tank sealants liquefied, causing catastrophic leaks. The solution required developing entirely new materials specifically engineered for high-octane fuel compatibility. Schmude collaborated with chemical companies to create synthetic rubber compounds resistant to aromatic solvents. Fuel tank construction presented additional challenges, requiring specialized welding techniques and alloy compositions that maintained structural integrity while resisting chemical attack. The Packard Merlin engine modifications proved equally complex. Standard pistons could not withstand the increased combustion pressures. Schmude worked with Packard engineers to develop strengthened pistons using improved alloys. Connecting rods and crankshafts required similar enhancements. The carburetor system required complete redesign for optimal performance with the new fuel mixture. Standard Packard Merlin engines in P-51 aircraft operated at 46 inches of manifold pressure using 100-octane fuel. The new formulation allowed sustained operation at 61 inches, with emergency power reaching 72 inches for brief periods. This represented a power increase from approximately 1,400 horsepower to over 1,800 horsepower. The additional power transformed the Mustang's performance across all flight regimes. The power increase came with significant engineering challenges. Higher combustion pressures generated more heat, requiring enhanced cooling systems to prevent engine damage. Schmude's team redesigned oil circulation systems and modified cylinder head cooling passages. They also developed new engine control systems that automatically adjusted fuel mixture and ignition timing to optimize performance while preventing destructive detonation under varying flight conditions. Engine durability became a critical concern with the increased power output. Standard engine components had been designed for lower stress levels and shorter operational periods typical of interceptor missions. The extended escort missions planned for the enhanced Mustangs would subject engines to high power settings for hours rather than minutes, demanding unprecedented reliability from every component. The fuel system modifications Schmude designed were revolutionary. He developed new fuel tank sealants resistant to aromatic compounds. Fuel lines used synthetic materials that maintained flexibility while resisting chemical degradation. Most importantly, he redesigned the wing fuel system to accommodate an additional 85-gallon fuselage tank behind the pilot. This tank, combined with high-octane fuel efficiency improvements, extended the P-51's range from approximately 400 miles to over 800 miles with internal fuel alone. Testing began at Wright Field in Ohio during spring 1943. Early results exceeded expectations. P-51 aircraft using 150-octane fuel achieved maximum speeds of 447 miles per hour at 25,000 feet, compared to 427 miles per hour with standard fuel. More significantly, cruise fuel consumption decreased by approximately 12% due to improved combustion efficiency. The combination of higher speed and better fuel economy dramatically extended operational range. The enhanced P-51 aircraft demonstrated superior combat maneuverability compared to standard variants. Test pilots reported that the aircraft could outturn most German fighters while maintaining speed advantages that allowed disengagement when necessary. High-altitude performance improvements proved particularly significant for escort missions, enabling interception of German fighters that had previously dominated at extreme altitudes. The psychological impact on German fighter pilots proved as important as the technical improvements. Luftwaffe interceptors had grown accustomed to engaging unescorted bomber formations after Allied fighters turned back at the limits of their range. The appearance of P-51 escorts over targets deep in Germany shocked German pilots and commanders. Suddenly, American bombers could be protected throughout their entire mission profile, eliminating the predictable vulnerability that German tactics exploited. Production challenges threatened to prevent operational deployment of the enhanced aircraft. 150-octane fuel required specialized refining equipment and quality control procedures that existing fuel production facilities could not provide. The Army Air Forces invested heavily in new refineries and distribution systems specifically designed for high-octane aviation gasoline. By late 1943, sufficient quantities were available to support limited operational testing. The logistical complexity of fuel distribution across global combat theaters presented unprecedented challenges. High-octane fuel required special handling procedures to prevent contamination and degradation during transport. Standard fuel trucks and storage tanks were incompatible with the corrosive properties of the new formulation. New transportation infrastructure had to be developed, including specialized rail cars, tanker ships, and storage facilities at forward air bases. Quality control became critical as production scaled up to meet operational demands. Even minor variations in fuel composition could cause engine failure or performance degradation during combat operations. Refineries implemented new testing protocols that examined every batch for octane rating, aromatic content, lead concentration, and contamination levels. Field testing equipment was developed to verify fuel quality at operational bases before loading into aircraft fuel systems. The first operational use of P-51 aircraft with 150-octane fuel occurred during bomber escort missions to targets in western Germany in December 1943. Results were immediately apparent. German fighter losses increased dramatically while bomber casualties decreased correspondingly. American fighter pilots reported superior performance in all aspects of combat: acceleration, climb rate, maximum speed, and maneuverability. The enhanced aircraft could match or exceed the performance of German fighters previously considered superior. Edgar Schmood's engineering team continued refining the fuel system throughout early 1944. They developed improved fuel pumps capable of handling the corrosive properties of high-octane gasoline. Fuel filters received special coatings to prevent degradation. Most critically, they solved fuel system icing problems that had initially limited high-altitude operations. These modifications ensured reliable fuel flow under all operational conditions. The strategic implications became apparent during planning for the first Allied fighter mission to Berlin. Military planners calculated that P-51 aircraft with standard fuel could not reach the German capital and return safely to bases in England. The round-trip distance exceeded 1,000 miles, beyond the range of any existing fighter aircraft. High-octane fuel modifications extended the Mustang's radius of action sufficiently to make the mission feasible with appropriate external fuel tank configurations. The Berlin mission represented far more than a symbolic gesture. German industrial production had become increasingly concentrated in the Berlin area as Allied bombing forced relocation from western regions. Aircraft factories, synthetic fuel plants, and critical manufacturing facilities surrounded the German capital. However, these targets had remained essentially invulnerable due to their distance from Allied fighter bases. German defensive planning had been based on the assumption that Allied fighters could not reach targets beyond a specific radius from English bases. The appearance of long-range fighters over previously safe targets forced complete revision of German air defense doctrine and resource allocation. Intelligence reports revealed the psychological impact on German civilians when American fighters flew over Berlin in broad daylight, demonstrating that German air defenses could no longer protect even the most important targets. Luftwaffe fighter pilot training programs collapsed under the pressure of defending against bomber formations protected by long-range escorts. German flight schools had previously operated in relatively safe areas of eastern Germany, beyond the reach of Allied fighters. The extended range of enhanced Mustangs brought these training facilities under attack, disrupting pilot production when the German Air Force desperately needed replacement aircrew. The cascading effects extended throughout German military planning. Army units could no longer rely on air support over extended distances. Naval operations suffered as coastal reconnaissance aircraft came under fighter attack. Allied bomber crews reported dramatically improved mission success rates once long-range fighter escort became available, with bomber losses decreasing by over 60% on missions with full fighter protection. Mission planning for the Berlin raid required unprecedented coordination between aircraft manufacturers, fuel suppliers, and operational commanders. Schmude worked directly with 8th Air Force planners to optimize fuel loading procedures and consumption rates. P-51 aircraft received maximum internal fuel loads plus external drop tanks, containing additional gasoline. The total fuel capacity approached 600 gallons, more than double the standard fighter fuel load. The mission launched from English bases on March 6, 1944, with 357 P-51 Mustangs, providing escort for over 600 bombers. This represented the largest fighter formation ever assembled for a single mission. German radar operators initially assumed the massive formation was another bomber attack until fighter aircraft began engaging Luftwaffe interceptors over German territory. The realization that American fighters had reached Berlin fundamentally altered German defensive strategies. Combat results validated Schmude's engineering innovations. P-51 aircraft using 150-octane fuel demonstrated clear superiority over German fighters throughout the mission. American pilots shot down 68 German aircraft while losing only 11 Mustangs. More importantly, bomber losses were significantly reduced compared to previous unescorted missions to similar targets. The escort fighters had achieved their primary objective of protecting the bomber formations. The psychological impact on both sides proved equally significant. German fighter pilots, accustomed to engaging unescorted bombers after Allied fighters turned back, found themselves facing fresh enemy fighters over their own capital. American bomber crews, who had endured months of devastating losses during unescorted missions, finally experienced the protection they had desperately needed. The transformation in crew morale was immediate and profound. The Berlin mission's success triggered immediate expansion of high-octane fuel production and distribution. Additional refineries began producing 150-octane gasoline specifically for military aviation use. Fuel transportation systems were established to ensure adequate supplies reached forward bases in England and Italy. By summer 1944, high-octane fuel had become standard for all P-51 operations over Europe. German intelligence quickly recognized the significance of the fuel improvements. Captured P-51 aircraft were examined extensively to understand the technical modifications enabling extended range and enhanced performance. German engineers attempted to develop similar high-octane fuels, but lacked the industrial capacity and chemical expertise necessary for large-scale production. This technological gap contributed to German Air Force decline throughout 1944. The German fuel shortage crisis became acute as Allied bombing targeted synthetic fuel plants deep in occupied territory. German scientists had developed synthetic fuel production to reduce dependence on imported petroleum, but these facilities required protection from air attack that the Luftwaffe could no longer provide once Allied fighters gained extended range capability. The destruction of synthetic fuel plants created cascading shortages that affected not only aircraft operations, but also tank units and naval vessels. German pilot training programs suffered devastating reductions, as fuel allocations were prioritized for frontline combat units. Flight schools that had previously provided comprehensive training were forced to reduce instruction hours dramatically. New pilots reached operational squadrons with inadequate experience, contributing to rapidly increasing casualty rates that further depleted German aircrew strength. The fuel crisis had created a downward spiral that German aviation could not reverse. The engineering achievement extended beyond simple fuel chemistry. Schmood's team had solved dozens of technical problems related to high-pressure fuel systems, corrosion resistance, and engine reliability. These innovations influenced post-war aircraft development and established principles still used in modern fighter design. The integration of advanced fuels with optimized airframe design became a standard approach for maximizing aircraft performance. The systematic engineering methodology Schmood employed became a model for complex technical development programs throughout the aerospace industry. His approach of identifying performance limitations, developing technical solutions, and implementing comprehensive testing protocols influenced everything from jet engine development to spacecraft design. Production statistics demonstrate the scale of the achievement. By the end of 1944, over 8,000 P-51 aircraft had been delivered with high-octane fuel system modifications. These aircraft flew hundreds of thousands of combat hours using 150-octane gasoline. Fuel consumption exceeded 50 million gallons annually, requiring massive industrial investment in specialized refining and distribution infrastructure. The tactical implications revolutionized air warfare doctrine. Fighter aircraft could now escort bombers to any target within their geographic reach, eliminating the sanctuary that distance had previously provided to enemy forces. This capability enabled strategic bombing campaigns against targets previously considered unreachable, accelerating the collapse of German industrial capacity and military resistance. Edgar Schmood's personal story adds human dimension to this technical achievement. The German-born engineer had fled his homeland in 1925 to escape economic devastation following World War I. His innovations ultimately provided Allied forces with the tools necessary to defeat the Nazi regime that had transformed his native country into a totalitarian state. The irony was not lost on Schmood, who considered his work a personal contribution to liberating Germany from fascist control. Post-war analysis revealed the full impact of high-octane fuel developments. German aircraft production declined by over 60% during 1944, partly due to bomber attacks on factories previously protected by distance from Allied bases. Fighter pilot training programs collapsed, as fuel shortages prevented adequate flight instruction. The combination of technological superiority and industrial capacity had achieved decisive strategic advantage. The legacy extends to modern aviation. Contemporary fighter aircraft use fuel systems derived from Schmood's wartime innovations. High-octane aviation gasoline remains essential for high-performance aircraft operations. The integration of advanced fuels with optimized engine design continues driving improvements in aircraft range, speed, and efficiency. Edgar Schmood continued his engineering career for decades after the war, designing aircraft including the F-86 Sabre and F-100 Super Sabre. His approach to systematic innovation and technical problem-solving influenced generations of aerospace engineers. The principles he established during P-51 development remained relevant throughout the jet age and into the space era. The impossible fuel mixture that enabled the Berlin raid represented more than chemical engineering achievement. It demonstrated how individual innovation could influence global strategic outcomes when supported by industrial capacity and institutional commitment. Schmude's work proved that technical solutions to military challenges could accelerate conflict resolution and reduce human casualties through decisive technological advantage. That March morning in 1944, when P-51 Mustangs appeared over Berlin for the first time, marked the beginning of the end for German air superiority. The impossible had become inevitable through the vision of an immigrant engineer who understood that the right fuel mixture could transform aviation history and help determine the outcome of the greatest conflict in human civilization.